So today we have a half day with the Near Lab tour happening this afternoon for those of you that are interested. Today we'll be talking about data management, talking about projects both large and small. So without further ado, I'll let you get going. I'll start.
Thanks, Adam. Morning, everybody. Yesterday we talked about projects, ways that you can get SQL functionality with small projects. We talked a little bit about trade-offs of going through the trouble of an overhead of automating stuff and you're not going to be sharing your data or doing a task over and over. Today we're going to be focused on the other side. What do you do if you have an LSST-sized project? And at the end, we can talk a little bit about the confusing space in between of what do you do if you have a medium-sized project where you know you're going to be using your data many times and maybe you have a few collaborators, but you're unsure of how much trouble to go through how much time to put into your data management. So yesterday we introduced this idea of indexing, and today we're going to talk about using this idea of partitioning to scale up databases and, more importantly, scale out databases. There's a couple of ways to do this. We're going to talk about parallel relational database management systems, which is what the LSST database is going to use. And we're going to go through the implementation for LSST database in a little bit of detail, since this is the LSST Data Science Fellowship program, and presumably you're going to be using the LSST database when it comes online. But we're also going to talk about another way to parallelize your databases, which there's been a lot of hype around these days, which is this MapReduce framework and the data management systems that have come out of it. We're going to introduce that and talk about the differences and trade-offs involved. So first, let's talk about scaling and how you would parallelize an operation or a database. You can talk about scaling in a number of different ways. The ways that databases have been parallelized in the past has been by scaling up. That is, just buying an increasingly more powerful server. So you guys probably at your institution have some giant machine with 200 gigs of memory and maybe 16 cores, or that you can run high memory jobs on, or something that requires a few nodes. So this is great, and these machines are really fun to work with, but they're also really expensive. So database systems have been running on machines like these for years, and the way to think of the benefits is if reading from disk is the most expensive part of your operation, then if you were to attach multiple disks to your computer, you would have multiple heads on disks, and you would get your throughput to be higher and your latency to be lower. In the diagrams going forward, these P's stand for processors, and this is just, you can think of this architecture as just a giant high-power computer, and we call this scaling up. Another way to get a little more parallelization is to have separate nodes all attached to a shared network of disks. M stands for memory at this point. So you can think of this as each of these as a separate server. The HPC systems that you run on are similar to this architecture, where you have individual nodes, but sometimes there's a shared network of disks mounted to them. For databases, this is difficult because the performance is mainly limited by the bandwidth of this network connection. So this is usually some kind of high-speed bus. And this will limit the number of nodes you can have. And in practice, you will really only see databases with 10 nodes. And Oracle dominates this space. To get even more parallelization, you can have what we call a shared nothing architecture. And this is the most parallel of them all, because you have a node, which is just a simple, cheap computer. You have processor, memory, disk, all self-contained. And you have these in some kind of cluster in a network together. And every node has a separate disk and is responsible for a separate piece of your data. This is especially powerful because you can get more processors for a cheaper cost. So some examples in the wild are Greenplum and Teradata, and this is also the architecture that LSST's Qserv database is going to use, which I'll talk about in more detail. And just to tie this into the definitions of scalability we were talking about yesterday, it's this shared nothing architecture that influenced this definition of scalability, that it works with thousands of cheap computers. Okay, any questions on parallel architectures? We're assuming we're going to be talking about shared nothing architectures going forward. Okay, so LSST's data management needs are fairly extreme and specific. We need it to be incrementally scalable. This means that you can easily add nodes to it as time goes forward. The reason this is important is because the data set's going to be growing over the course of the 10-year operations, and we want to be able to grow the database along with it. Obviously, we want it to be reliable and available. One very astronomer-specific need is that it needs to be low cost. This was why the Teradata and Greenplum solutions were prohibitively expensive for us, and we ended up going with a requirement of everything. All the components of the database have to be open source, so that members of the team can maintain this over the course of 10 years. From a technical standpoint, we want table scans to be able to complete in an hour. We want small data, needle in a haystack type queries to return in less than 10 seconds, and that even seems a little long. I'm hoping that it's much shorter than that. And another astronomy-specific need is this need for spatial self-joins and cross-matching, which has motivated the partitioning system for the LSST database. So we're going to have tables that are 10 to the 9, 10 to the 12 rows. And if we want to take one of these tables and spatially match it to itself, that is, find all the objects that are, you can think of it as finding all the different observations of the same object, so duplicates, but based on their position. This would take naively n squared operations. So you're talking about 10 to the 20 operations. So this needs to be optimized. The way that this is implemented is as follows. we're using a cluster of MySQL instances. So every node is going to be running its own copy of MySQL. Each node is also going to be responsible for one partition of the data. In theory, you could query each node and it would be like having access to a smaller, scaled-down database. But that interface isn't going to be made available to the public. So what you're going to do is submit a query to the website, and then it's going to be picked up by the distributor. The distributor is going to take your query and then translate it. It's going to translate it into either 1 or 100 subqueries to send to each of these specific MySQL instances. Each of these MySQL instances are going to return a result set. That result set is going to get transmitted to a combiner, which will concatenate your results and send them back to you. We talked a little bit yesterday about partitioning. And specifically, what good fields are to partition your data for astronomers, specifically spatial coordinates. We very often do seeks based on position in the sky, and are looking for ranges and position in the sky. For this reason, Oserv is going to partition the data by position. So each database will be a self-contained LSST, but focused on just one region of the sky. So ideally, if you were just doing a query like we were doing yesterday of return me all the objects that are within an arc minute of some source that I'm interested in, that query is just going to get translated into one subquery, gets sent to one node, and only one node is going to be responsible for fulfilling your query. So we're hoping that this is going to provide some efficiency. Not all parallel database systems use this system of partitioning based on ranges. Can you think of why in industry this might be a bad idea? So in industry, most of these databases are focused on transactions, and so you're looking for particular rows in large data sets. Say you want to spread the load. You want to spread the load as evenly as possible across your nodes. So you can think of a scenario where the most recent transactions or the most recent occurrences are more popular than stuff in the past, or there can be patterns where one node gets hit really hard and other ones are ignored. So to balance this out, what Teradata does, for example, is they use a hash. They hash the primary key, and then based on that hash, they send all the data to different nodes. So it's completely randomized, and the theory behind it is that without any further information about how your data is going to be used, it's best to just randomize it as best you can. So other than the spatial partitioning, one fun feature of Oserv is its shared scanning. We talked yesterday about how indexes don't help you all that much if you're returning large amounts of rows. So we're expecting a lot of table scans of the LSST database. It's going to be a huge database, and it's going to start getting expensive if we do a table scan for every query. So what it's going to do is accumulate queries that you submit, the queries that require a table scan. And once you have enough, it'll initialize the scan, and say it collects 10 queries. As it scans through the data, reading in each page and processing it, it's going to fulfill all 10 queries simultaneously to reduce the number of reads to disk. Which is a neat optimization.
I have a question about that.
Yeah.
So if I don't have a specific science example, but suppose there's something that I'm actually truly the only person that cares about that thing.
Mm-hmm.
So I've written a query that doesn't essentially line up with any other person's query. Is there like a long wait time for it to be executed, or how is that handled?
If it's a seek on with a spatial component, it'll use the indexes and return immediately. If it's not spatially dependent, then there are requirements in the amount of time that you have to wait. I think it's an hour, but if you submit a query that requires scanning through all of one of those tables, your query will be waiting for an hour.
Okay.
I should say up to an hour. Okay, let me motivate NoSql databases. So these parallel databases are great, but what if we wanted to run a job on not 1,000 nodes, but 10,000 nodes? Under the assumption that a server will fail once every 10,000 hours, and your job takes 4 hours to run, then you can be sure that a node will fail and your job will not complete, and you'll have to restart it. This problem of fault tolerance doesn't come up as much in traditional database systems because the assumptions are that your queries don't take as long as an hour. They usually return in seconds. And also they traditionally ran on fewer than 10,000 nodes. So Google employees were having this problem in the early 2000s. They were performing these very straightforward computations on their stockpile of web data. And it was a challenge for everybody to parallelize their computations, distribute the data, and manage the failures when they occurred. So what Google did was come up with an abstraction and framework that handled all this for them, so that all the employees had to do was plug in the logic, the functions that they wanted to run, and everything else was done for them. So in 2004, Jeff Dean published a paper called MapReduce, describing this system and framework, which caused a big splash. And 4 years later, there was a open source implementation released by Yahoo, and later adopted by the Apache Software Foundation. The Apache Software Foundation, you'll see a lot. They're a volunteer-run organization that supports and incubates open source projects, and most of the big data systems are supported by Apache, the open source ones at least. So this MapReduce framework also runs on a distributed file system. This file system, it has a logical tree for your data, but under the hood, it is distributing your data across all the nodes in a random fashion, and will even duplicate it up to 3 times for fault tolerance. So if you submit one of your jobs, one of the nodes goes down, 2 of the nodes go down, your data is still safe, and your job can still complete.
So is there a particular motivation for 3, right? That seems kind of random. Is that a certain percentage of failures?
I
They like other C cloud.
Hmm?
They might like other C cloud. The books where he makes 3 copies of everything.
Yeah, I'm sure you could do an order of magnitude computation on the likelihood that three nodes that all share one piece of data would go down. Is probably as well. Okay, I'm going to go into the MapReduce framework in more detail, and in the exercise after the break, you're going to be fitting some questions or problems into this MapReduce framework. Because if your question or problem can be formalized this way, it means that you can you have a lot of parallelization available to you. And this is also the basis for a lot of the most of the NoSql systems. So what MapReduce is, it's a recipe. And it follows this recipe of 5 steps in strict order. Each node is assigned some data, which is read in by the node. And then you apply a function. You map a function to each chunk of data. This function is just something, just to extract something you care about from each record. Then the MapReduce framework will take your results of the information you extracted via the map function and sort them and shuffle them for you. The shuffled data will then each go to its own node, such that each node is now responsible for handling like collections of data. You can think of this as a group by. And then you write a function that aggregates this list that's been accumulated by, that has been emitted from each of the mapper functions. And then finally, they get written to disk. So this read, shuffle and sort, and write steps, those are all handled for you. You can't change those. All you have to do is write a map function, something to extract something interesting from each record. And this reduce function, which is once you have grouped all of these records that you're interested in, how to summarize them or aggregate them, filter, or transform them. I've been talking about the data kind of ambiguously here, but it has a specific data model, which we call a key value pair, and you see these again and again in NoSql databases. All it is a key, some way you want to, it's your label for your data, and a value. A value could be anything. It could be an entire document, it could be a number, it could be a record. So all database rows can be expressed as key value pairs. However, not all key value pairs are database rows. So these are, you can think of these as a superset. It's a data model that's a superset of a database row. And this will become clearer in the example and in the exercise. So you have to formulate your input in terms of key value pairs and your output in terms of key value pairs. I want to go through an example of what this looks like in more detail. Say we have a petabyte of documents, and we want to do something simple, like count how many instances of the word "the" there are in these documents, or how many instances of the word "bus" there are. So each document each mapper function, or each document gets a map function applied to it, or mapped to it. So in our case, the key here is some kind of document identifier. Let's call it the file name. And the value here is the entire document. We can extract the interesting information out of this by splitting this document into words, and then returning or emitting, and it's different than returning. A new key value pair with the key, which is now just the word that you're iterating on, and the number 1. And so if we have the sentence, the bus went by, we would emit the 1 bus 1 went 1 by 1. Then the shuffle and sort phase will handle this for you. It'll take the results of all the mappers and find all the key value pairs with the key all the key value pairs with the key bus, and funnel those to one node. And that one node is going to be responsible for taking that key and new list of values and aggregating those somehow. So in our case, let's say there were, in all the documents, 3 instances of the word bus. We would get the reducer function responsible for the key bus would get bus and then a list of 111 in the list of values. So what we would want to do is sum those up and return the total. To see this a little bit more graphically, same idea. Your input is a key, which is your file name, your document ID, and then your value is your document. Your mapper function, which just splits all the words up and attaches the number 1 to them, runs, and then the shuffle and sorter will funnel these to separate nodes and separate mapper functions, which will aggregate these for you. In the, yeah.
I just want to make sure I caught that correct. The mapper function is the document?
The mapper function gets the
Gets
document as its value that it's responsible for.
Okay.
And then you can write the mapper to extract whatever you want from that document.
Yeah, honestly, I don't understand the difference between the emit versus the return.
Oh, so it'll emit, return would end the function, but a mapper can emit unlimited number of key value pairs. So it'll just, as it's processing the data, it'll just emit a key value pair, and all that means is it's the internal way of sending it into the shuffle and sort portion of the algorithm. So that part is all handled for you. And in the exercise, there will be it'll all be in Python and all on your machine, but there's going to be a simple class that implements this concept of emit for you. Yeah.
So the mapper functions that you define have to be like logic sort of equations or conditions or filter things?
Yeah, you can think of them as filters. They can be really anything. I mean, so let's reframe this question as let's make a histogram of word length. So how many words in our collection of documents have word length 5 or word length 6? How would we change this mapper function to be able to do that? Idea. Yeah.
So instead of having the W in intermediate, you could change that to length of W.
Yeah, exactly. And then you're going to have a much fewer number of pairs because there's more words in the document than there are word lengths in the document. And then what's going to happen is, so that your key now is going to be 1, 2, 3, 4, 5, and then you'll still have your ones, but you're gonna sum those up, and that'll be the total of words that appear that have length 1, length 2, length 3. Yeah.
So suppose your document was bus, 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 bus. So why would you not aggregate all those buses and then send out bus, comma 5, or however many buses you have? Why would you send out? Would you just send out bus 1, bus 1, bus 1, bus 1, or?
No, you're right. In practice, what people do is you can still do it in this framework, but you can apply your reducer function before sending it to the shuffle and sort algorithm. So in reality, like you said, each node has the ability to aggregate the documents that it is responsible for, and you can reduce your network load by aggregating these ahead of time, and you would definitely want to do that. Okay. So MapReduce caused quite a splash because it provided this framework for fault tolerance and data processing without all the additional database functionality. And so if you didn't need this extra database functionality, this could be very useful to you. But without things like indexing and schemas and the declarative language SQL, this was limited in its usefulness. So as a timeline of what happened afterwards, the Hadoop release, the open source came out, people started using it. Almost right after, a implementation of relational algebra called PIG for Hadoop came out. And then an implementation of the actual language SQL that runs on Hadoop came out. And okay, fine, but we still don't have indexing. So indexing was developed, schemas, and ultimately transactions, which I highlighted because I was planning on talking about, but it might not. If you guys are interested, somebody ask about it. But my point is that this framework came out, everybody was super excited, but then realized that in order for it to be truly useful, we needed to start adding these things, these features, and by the time we were finished adding features, this is starting to look very much like a database. And we see this pattern in technology again and again, where something that claims to be super new comes out, and everyone says, oh, but it's missing this, and oh, and it's missing that, and you end up rewriting something that has been around for decades, and re-implementing ideas that have been around for decades. So this is the basis of NoSql databases. There have also been papers that have gone in other directions, notably being this paper that started Spark. So Spark, so MapReduce was also limited in that you would run a job, but had no access to the intermediate results. And if you had some kind of iterative computation, like you often see in science pipelines or machine learning pipelines, there was no way to use intermediate results to iterate. Likewise, if you wanted to have a more interactive, MapReduce wasn't very interactive. You submit a job, there's a lot of overhead, it takes a while to complete, and you can't go back. And it handles all its inputs and outputs by writing them to disk. What Spark does, so if you think of MapReduce as a way of managing the processors and the disk across your cluster, Spark is the way to manage distributed memory across your cluster. So now with Spark, you have access to, you can think of them as these resilient distributed data sets across all your nodes, and have a more interactive experience and do processing with iteration. And this Spark is the darling of the big data analytics community at the moment. And if you were to learn one of these systems, at the moment, this is the tool that I would recommend. However, remember the warning from yesterday. The timelines, the timescales for these tools to come in and out of fashion are extremely short, way shorter than Git and SVN. The development time for these are extremely rapid. So in 3 years, there might be something else that everybody's going to be using. If you guys are interested, I can go through a demo of it on Friday. Okay. So since then, a lot of database systems that are based on this MapReduce framework have come out. The concept of NoSql is somewhat hard to define, and nobody likes the name NoSql. The name was an accident, but unfortunately it stuck. The way I think of them is maybe no relational. They don't have tables, and they don't have. It's just a different data model. Whereas it's hard to define NoSql as a whole. We could say that they have some things. We have some things in common we can use to characterize them. They have no schema. They're not relational. It's key value pairs, document stores, column stores. The implementations of these are all a little different. For example, a document store has a key, but the value is a document. The cool thing about these is that the database can actually inspect the document and pull specific pieces of information out of it. It's usually in some kind of format like JSON or XML. Key value stores, on the other hand, the value is a black box. It's just a blob. The database has no idea what it is. It could be anything in there. It could be an image. It could be a document. It could be a database row. It could be anything. Column stores are maybe the most complicated data structure of them all, and I'm not sure I can explain how it's different at the moment. It stores. It essentially reduces to a key value, some kind of aggregate orientation as well. So the differences between these are subtle, but they have something in common, which is that they are aggregate oriented. And by that I mean you have a key, and then you have some aggregate, some collection of data that you can't separate. You can't slice and dice it like we could with relational databases. So another feature is that most of the systems are open source. Google keeps coming out with new systems. For example, Bigtable, and then an open source implementation will come out soon afterwards. Another feature, this is what they were based off of, is that they're fault tolerant and easy to run on clusters with tens of thousands of nodes. And they evolved from companies that work with really large web data, like Google and Facebook and Twitter. So putting this concept of being aggregate oriented again into context of this example that we used yesterday of astronomers, people, and their publications. This in one of these key, NoSql databases, for example, your key could be a person ID, and then the value is just a collection of information about this person. So it could include their publication list, their institution. There's no guarantee that every value will have the same collection of data. This is what we mean by schema lists. This puts a burden on the application programmers, because you can't assume that data is going to be in your records. You have to write the code that handles that. But what I wanted to point out is that this aggregate orientation looks a lot like this object-oriented programming model that we talked about yesterday. And you can think of it as related to that when you're mapping out your how to model your data. So some features, we already talked about fault tolerance and the lack of schema. We talked about the bad parts of having no schema. The benefits to having no schema is that it makes it easier to work with your data immediately. Have you guys ever ingested data into a database from a flat file? Or who's done that? Yeah. So you'll know that your data file won't always immediately fit the schema that you have defined for it, and it's not always a trivial task. So you front load this task of ingesting your data into a particular schema. The benefit you get out of it is that your application code can depend on those fields having those data types going forward, but getting your data into that format can sometimes take some time, as you might have found. And another benefit is this idea of user-defined functions, which Simon asked about yesterday. On relational database management systems, people write compiled functions to add to the database. We saw the SciSQL ones yesterday. You worked with some special ones from SkyServer yesterday. Those are the ones you worked with are probably C#, a combination of SQL and C# functions. The ones that we saw in the MySQL database were C functions. These have been, they're not difficult to write, but they're also, there is some overhead in compiling them and applying them to your database. And some people find this a pain in the butt. So in these NoSQL systems, it is a lot easier to plug in your own code into this data processing model. A question we often get is why isn't LSST using one of these systems? There's not enough database functionality at the moment. So we need joins, we need indexing. To run it as a Hadoop job, there's an overhead to starting the job, and so we wouldn't get the same super low latency for these spatial seek queries that we want. But the most important reason from my perspective is that the photometry catalogs already have a well-defined relational model, and why would you want to throw that away for a more why would you want to throw that away for a more flexible system when you already have very well structured strict outputs from the science pipelines? Okay, so this is my last slide, and I kind of wanted to turn this into a discussion of data management in general and summarize the last couple days. You'll work on a lot of different projects, some of them small. You go on an observing run and collect some data that it'll take you maybe a week to analyze, and only you are interested in and will use. And then on the flip side, on the other side, you have an LSST size project where you have hundreds of people on the project team and thousands of potential users. Obviously, in this space, you're going to invest a lot of time into data management. The area where it gets more questionable is in the middle. So what do you do if you have a project with maybe your science group at your department, and you want to work on this data together? Maybe it's terabytes. How much time do you invest in your data management? And I've seen groups handle this a number of different ways. So for example, Julianne Del Canton's group at UW have a survey of the Andromeda Galaxy taken by HST. What they did was process the data on Amazon Web Services rather than buying hardware to process it. And there were some trade-offs to this. They found it wasn't, everybody complains about Amazon Web Services being expensive. It did get kind of expensive, and they were able to make it cheaper by using spot instances and whatnot, but there were trade-offs involved with that as well. Something that we have done, LSST has done in the past for processing its validation data sets, its data sets for testing the stack, is just to use regular HPC clusters that are managed, the national scale ones run by Exceed. So TAC, for example, is an Exceed cluster. And this has worked well for us in the past too. I would be happy to talk to you guys more about that, about having shared databases on HPC clusters and whatnot. But I was wondering if what you guys have done in the past, or what your thoughts were on what you do for these medium-sized projects, or even the instructors, what you guys have done in the past with your medium-sized projects. Yeah.
So I think that for at least the medium-sized project that I'm on, that's a little bit bigger than medium-sized, is like breaking it up into different smaller collaborations within that. Mm-hmm. So for example, like I do radio, right? So we have a continuum component and we have a spectral component. So that data kind of gets broken up, and like each of those groups kind of takes on what they need to from that.
Cool. Do you guys store it on university managed
It depends. So like, I think the spectral component puts it mostly on NRAO machines, but then other people put it on like, yeah, more like home institution HPCs.
I mean, I guess here for the stuff I'll be talking about tomorrow, we have a small little cluster of our own. And this is really nice because we're still in the development phase, right? We're putting things together and breaking things more often than not. And consequently, you do want to have the freedom to muck around and solve what you need to quickly. And something like Amazon Web Services is nice once you have a mature product that is version 1.0 or something of that sort. You don't have to. It's well tested, well validated, and works reliably at that kind of scale. So that is one of the plans that we have going forward. But initially, at least, adding something like start working on your local machine is really, really helpful.
Yeah. Eric?
So with that in mind, I don't know if maybe either of you have thoughts about this. I mean, often it's difficult to make that transition, right? I mean, really the 3 jumps are sort of from your laptop, 2 jumps, I guess. From your laptop is where you start. Then you move to like your local thingy that's sitting underneath your table or something like that. And then you move to the scaled up cloud server, whatever, you know, maybe in CSA or whatever, you know, cluster scale. Do you have any thoughts about how to make that transition easy? Like tool sets that make it a lot easier to move from all of these things without having to spend hours or tons of some other FTEs on it?
Yeah, so the point where you decide that this project is ready to be shared with more people, or if you were testing on a small set of data to apply it to the full data set.
I would say work with CS people and have them take care of that problem. This is why they exist. And they are much better at this than astronomers will ever be. They write well-modularized code that's documented. So if you want to like make the transition from I need to submit some jobs on my little cluster that runs Slurm to I need to run on Amazon Web Services, they simply switch off one little module and then magically works, and you don't have to change any of your stage code, which you hopefully did not write in such a way that you depended on the architecture. This is really why the computer scientists are wonderful human beings, and you should thank your IT department all the time, thank and work with them.
The problem you're describing. The problem you're describing is good motivation for the scalable systems and your local systems to look similar, to make that transition easier.
Yeah, so I guess I'm more wondering, do either of you have thoughts about what that actually looks like, right? I mean, one thing that means is you don't open local files on your disk all the time, because that's clearly not going to scale. But are there frameworks, or like you think we should always be using containers or something?
Yeah, containers are a lesson for another time. They're an interesting thing.
I don't know if anybody's going to be talking about Docker or anything like that. That's not clear.
Yeah.
So I tried Hadoop on tech, and I always need to load my data to the file system and then run whatever I want, and then collect the data back from the system. It's not so fun if I have a huge data set. So maybe LSST data will be like Hadoop ready. I mean, it's already loaded there, and people just need to read their own like mapper and reducer or whatever thing, and it can be. But then
that's an interesting idea. We're already storing the data in a parallel database and optimizing it for reads through for queries, these SQL queries. There will be copies of the database in various data centers. There's been no talk of making a copy on a distributed file system in raw files that people would be able to process individually. My thought is that that might get prohibitively expensive and complicated, but but you will be able to download very large portions of it, and you will be able. I mean, you could make your own copy of the LSST database if you really want. The other thing is that in 5 years, we won't know what tools people are going to use, and we don't want. So SQL will definitely still be around. It's been around for decades. It still fits this problem really well. These types of SQL engines on Hadoop, like Pig and Hive, they're already falling out of favor, and so we wouldn't want to support that specifically. But if there's something in 5 years that everybody's into, we will at least consider facilitating it. Yeah.
So I have a question on something from earlier, which I maybe just missed, but you said one of the primary motivations for moving to something like MapReduce or Hadoop, whatever you want to call it, was that you have the fault tolerance for in case a portion of the query or portion of the query breaks.
Mm-hmm.
But in the diagrams you were showing, I didn't see actually how you, if something breaks, how you recover that.
Yeah, that is an important part of MapReduce. So say when this node is mapping this data set, it goes down. It pings a master server. The master server becomes aware that it has gone down. If it doesn't heard from it in a while, it'll just assume that it's offline, and it'll assign a new node to this data set, and it manages which data sets get applied to which nodes. And so it'll, without you even needing to handle it, it'll restart those tasks and just redo them for you. So it can redo any task that hasn't completed.
And is there, that's, as far as I can tell from that description, that's sort of outside of the actual mapping and reducing.
Right.
So is there a reason why you couldn't implement a similar thing for the sort of parallel databases you were talking about before?
Oh. Yes, and so I don't, that part of them I understand. They are definitely fault tolerant, but I don't know the mechanism by which they do that. There is some data duplication, and there's overlap. There's overlap amongst the partitions spatially. So that the reason for overlap in the spatial partitions. So two partitions. What I mean is two partitions will cover an overlapping part of the sky, and the reason for that is if you're doing a search that extends beyond the edge of a partition, you don't want to have to split that into two queries when you can do it in one.
All right, are there any further questions for Yusra? All right, with that, let's please thank her.